So in this segment, we'll begin a discussion of transaction isolation levels, and we'll finish it in the next segment. It's common for two different programs, or perhaps two different threads of execution, to access a database simultaneously in two different transactions. A typical web server, for instance, handles multiple requests at once, each on a different thread, and several requests may access the database at the same time via different connections and transactions. And this thus invites an important question: what happens if two such transactions modify, delete, or insert data into the same tables and rows at the same time? What keeps them from interfering with one another? And the answer is isolation, the I in ACID from the prior lecture. But it's a complicated answer because there are several different types or levels of isolation, offering trade-offs between efficiency and the degree of protection against interference between two simultaneous transactions. And just to make it even more interesting, adding to the complexity is the fact that while there are 4 standard levels of isolation defined in general in the field, each DBMS implements the 4 levels slightly differently. So any discussion of isolation levels is necessarily a bit database specific. Now, let's go through an example that discusses all 4 levels and illustrates them using the same account table as in the prior segment. And we'll describe the formal definition of each level and then illustrate how they actually work in MySQL, which will differ in some cases a bit from the formal definition. We'll start with the most relaxed isolation level, which is read uncommitted, and then we'll move steadily upward to the most restrictive, which is serializable. Now, our example will have 2 connections, as you can see here, running at once. And we can do that by opening 2 simultaneous MySQL client sessions. You should try it yourself to follow along. We'll call these session 1 up here and session 2 down here. As the comments in the attached SQL file, transactiontest.sql, indicate, session 1 is going to want to add $50 to account 3, and session 2 is going to want to add $100 also to account 3. Each session thus needs to get the current account 3 balance, as we'll see here. We'll do a select star on account to find that, and then update account 3 to reflect the added value. Now we'll repeat the example for each level of isolation, and on the first 2 levels we'll also have session 2 make an error and then do a rollback to illustrate how isolation works with aborted transactions. To set the isolation level of a transaction, each session performs a set transaction isolation level command like this, with the level following, like read uncommitted. So session 1 begins by starting a transaction with read uncommitted isolation, and then session 2 follows by starting a similar transaction and then checking the current account table contents and adding 100, well, but mistakenly adding 200. So let's go now to the actual sessions and see this happen. And by the way, I just did a reset to the initial state. I had some old data in there in the earlier part of the segment. But we're now at this point where we were at the end of the prior segment, and we're going to apply those to initial transaction starts. So here is session 1. And then session 2. Okay. Now, session 1 will check the account table preparatory to doing its own addition of $50. And what it sees is session 2's incorrectly increased $900 value. And that brings us to question 1. That session 1 can see the $900 is a little surprising given the nature of transactions. Why would I say that? And the answer there is that session 2's transaction is not yet committed. It's uncommitted, and thus it really isn't in the database yet, officially. So apparently in read uncommitted you can see uncommitted data, and we'll talk about that in a minute. But for the moment, let's have session 2 roll back its transaction, realizing it made a mistake, and then see what happens in session 1. A second select star now sees the original $700 for account 3. The brief view that session 1 had of that uncommitted $900 value is termed a dirty read, because in memory cache terminology, data that has not yet been written to permanent storage is called dirty. Read uncommitted isolation is so called because it makes even uncommitted data readable by other transactions. Any data your transaction reads in this isolation mode may be some other transaction's uncommitted work, retractable via rollback at any time. Now, as you can see in the SQL file, we're at this point down here now. Session 2 is going to restart the transaction and try again, and we'll do the job properly. It'll correctly add $100 to account 3 and commit the result. And here's the actual performance of that in the session. We restarted our transaction and added our $100, and now we've got $800 in the account. Now, session 1 is, of course, still in the middle of his transaction, right? And what he's going to do now is take a look at the $700 that he saw most recently and increase that to $750 to do his add of $50 to the account, and then commit that change. And now, if we do a select star from account in either session, we've got $750, and session 2 is wondering what the heck happened to his $100. If session 1 had done a select star right before adding the 50, it would have seen the 800 and increased it to 850 instead. But session 1 relied on its most recent data that showed account 3 at 700 and wrote the 750 into the account, overwriting session 2's 800. Right? So this isn't a case of a dirty read. No uncommitted data was read here. Instead, session 1 relied on data that became out of date during session 1's transaction due to a commit by another session. Session 1's read of $700 for account 3's balance is a non-repeatable read. It's committed data when it was read, but it might change at any time due to further commits. So a later select by session 1 may read a different value, even though session 1 itself did nothing to change the value. Question 2. Could session 1 have reliably fixed this problem by just doing another quick select right before updating account 3's balance? We said that it might have just a minute ago, but note the adverb reliably. That's the critical point. Why or why not? Why couldn't it have reliably avoided overwriting session 2's $100 addition? And the answer is, well, no, not reliably, really. Because if session 1, read the $800 after session 2's commit, then the problem would be solved. But there's no way that session 1 can be sure that session 2 is done. Session 2 could delay its commit arbitrarily and then sneak in the commit between session 1's most recent select call and session 1's commit. And thus, session 2's update could still be lost. It's all a matter of timing. Now, question 3, since we're thinking about the way that different transactions could time relative to one another, what timing, if any, would have caused the loss of session 1's change and kept session 2's change? And the way that would work is if session 2 held off on its commit until session 1 had committed, and then session 1's data would have been overwritten by session 2's commit. Basically, the last session to commit wins. So, in summary, read uncommitted isolation permits both dirty reads and non-repeatable reads, with associated possible problems. It's the most efficient isolation level, but also the sloppiest. It's useful when you're only looking at data, perhaps to do general statistics, and you're not too concerned with perfect accuracy, nor with ensuring that any modification you perform is based on repeatable data. Now, the next higher level of isolation, read committed, precludes dirty reads by ensuring that other transactions never read uncommitted data, only committed data, and thus the name. So we're going to repeat the sequence of operations that we just did, but under read committed isolation. So starting with session 1 here, we'll begin a read committed transaction. And then we'll do these commands in session 2. Note that we'll need to increase the balance to $950 to make the $200 mistake, since it was now $750 that we started with from the prior work. So here's session 2's $200 mistake. But now the first select from session 1 does not see the $950. It is not looking at uncommitted data. And session 2 can do a rollback of that mistake, and session 1 will be none the wiser. MySQL accomplishes this, by the way, by arranging for session 1 to see an original copy of the data and for session 2 to work on a temporary version prior to committing. But a different DBMS might have done this instead by putting a lock on the account 3 row once session 2 had even temporarily altered it, and then making session 1's first select wait until session 2 either committed or rolled back the change. MySQL uses row locking like this in higher levels of isolation, which we'll see in a bit. Now, importantly, read committed isolation does not solve the non-repeatable read problem. Session 2's $100 edition will still be lost due to session 1 using the non-repeatable $750 value. So session 1 is still looking at its $750, and session 2 does its now correct update to $850, but session 2 doesn't realize that its read was non-repeatable, and it thus updates to 800, and once again session 2 is left wondering what the heck happened to its $100 edition. Now, to avoid non-repeatable reads, we need the next level of isolation, repeatable read, which we'll discuss in the next segment.